A tremor is an unwanted movement or oscillation of one or more regions of the body attributed to neurological disorders or problems in the brain centers that control the movement of particular muscles. There are many illnesses that result in tremors, such as multiple sclerosis, Parkinson's disease, traumatic injury to the brain, and strokes. Essential tremor, which affects 5 to 10 million people in the U.S., is a progressive neurological disorder. Its most recognizable feature is a tremor of the arms, which is most apparent in voluntary movements, such as eating, writing, and typing. These actions are all necessary in an office environment. Tremors themselves aren't fatal, but can significantly restrict a person from doing the simplest of tasks in their workplace and in their daily lives.
To formulate a design for our device, we first researched the products already on the market and found many issues. Mainly, the current products severely limit movement and are too restrictive and cumbersome to prevent tremors. We sought to build an inexpensive device that would allow for adequate arm mobility and limit the effect of tremors by providing natural resistance to movement in order to stabilize the entire arm.
Our final design features a back-driving motor attached at the elbow to provide a natural resistance. The motor rotates when the arm is in motion when accomplishing a certain task, such as typing or writing. The brace spans from the wrist to the shoulder. The entire device is foam padded for comfort and can be attached with the free hand using Velcro. The device requires no electricity, maximizing the usability and safety of the design. TRAB moderates the effects of tremors and significantly improves the user's ability to perform tasks that require fine motor control.
The construction of our device was divided into 4 parts. To construct the arm brace, we first cut the aluminum strips into 2 sections. One of the sections was used for the upper arm, and the other part was used for the forearm. We connected the 2 parts via a step motor and 2 gears. We used screws and bolts in order to attach the step motor and gears to the 2 separate pieces of aluminum. This formed the basic skeleton of the device. Then, Velcro was attached onto both the upper and lower arm. This allowed the braces to be attached to the person's arm. The Velcro was attached with adhesive material and was adjustable in order to provide the greatest amount of comfort.
A set of pads was attached to each piece of aluminum in both the upper and lower parts of the brace via screws as well as adhesive material to provide comfort as well as stability to the arm. Finally, the arms of aluminum and the step motor were adjusted so the right amount of resistance was provided. The bolts were loosened slightly in order to allow for the device to rotate successfully. This was the final step in the construction of the device.
To ensure the functionality of our device, we performed various tests. First, we tested the comfort and usability of the device by trying it on various team members. The device moved with ease and provided ample resistance to movement. It was easily adaptable to members with different arm sizes and muscle power. The second test sought to determine whether the device limited the effect of unwanted arm movement in an objective arm model. To ensure precise and systematic testing, an arm was constructed out of aluminum tubing and PVC piping. We attached the device to the makeshift arm and systematically oscillated the upper and lower parts of the arm to simulate tremors.
The resistance of the brace was measured using video analysis. A test subject rotated his arm from the elbow joint as quickly as possible with and without the brace on. A high-speed camera was used to capture the details of this motion. As shown, the angular and tangential velocities of the arm with the brace on are clearly lower than without the brace. This shows that the resistance provided by the brace is significant in reducing the rotational motion of the arm, making the brace suitable for minimizing involuntary tremors.
The motor operates without electricity, thereby decreasing costs and avoiding the potential risk of circuitry. Cushions as well as Velcro strips were attached along the length of the device to ensure comfort and stability. TRAB features a relatively simple design. Only a few materials were used to construct the device: aluminum sheet metal, gears, motors, Velcro, and cushions. The malleability of aluminum means that the device is adaptable to arms of different shapes and sizes.
TRAB can be implemented on a large scale quite easily. Such a device can be used for everyday tasks, from using a computer to cooking in the kitchen. Current products on the market are inadequate. There are some braces which severely limit arm movement and others which are simply ineffective against essential tremors. TRAB solves these problems by allowing for adequate arm mobility, while variable resistance, not static resistance, is produced by the back-driven motor, allowing the device to be more effective against tremors.
The attachment of device onto arm is highly universal. Velcro is one of the easiest, cheapest, most universal materials to work with. Also, A tremor patient would not have difficulty with Velcro because it is secure but not stiff enough to require a lot of force. The device is also light and durable because aluminum is a lighter metal, but many different metals can be used in replacement, such as plastic. These main structural elements can also be cut to different lengths to accommodate different people. The central bolt in the design can be tightened or loosened to provide varying levels of resistance to the user.